Recently, Anthropic announced that they were going to watermark their text output. And I thought, well, what better way to talk about this topic than to just read 2 papers on how to do it. But before we do that, I have on screen something that was generated from Gemini, so it's image generation. And I'm going to use this as an example to talk about what functionality makes a good watermark from the context of image and how it applies to text. So firstly, if we just want to see the watermark, it's fairly straightforward. We look at our threshold, and as we increase it, it will get to a point where all of a sudden you'll be able to see the watermark. And this watermark, whether we crop the image, whether we resize the image, whether we change the brightness or the contrast or the saturation of the image, this watermark will remain. So we want our text generation watermark to be invariant to things like, if they just took the middle sentence or just the last sentence or the first sentence, we should still be able to detect the watermark. So with that in mind, what I'm going to do is I am going to show you some examples. Let's bring up the examples. So here's the example. I have a liquid 2.5 model, 350 million parameters, and I asked it the question, what is a rainbow? And I have 3 generations on the screen. So the task for you is to have a look at them and see whether you can tell which generation was used. There's 2 different types of generation. It was either generated with a watermark or generated without a watermark. So the goal is to find which 2 use the same approach, and if you can identify it, of the 2, what kind of approach was used. And just for clarity, the last one does have 2 different blocks of text. So with that in mind, let's have a look at the very first approach. The very first approach comes from the paper, A Watermark for Large Language Models, and it came from ICML 2023. The high-level idea is fairly straightforward. We have our token set and we split it into green and red tokens with equal probability. So that means half the tokens are going to be assigned to be green tokens, half the tokens are going to be assigned to be red tokens. And when you do your generation, you want to boost the probability of the green tokens, and decrease the probability of the red tokens, which means that when you generate it, you should see more green tokens. When there's no watermark, we should see equal probability of green and reds, and when there is a watermark, we should see a higher probability of greens. And with this kind of approach, it's pretty easy to come up with a z-score and a p-value, because the hypothesis testing is to test whether the number of green tokens is 50% or not. So if we look at the algorithm with just a little bit more detail, there is a little bit of a complexity that they add, and that is the hash of the token is used as the seed for the random number generator, and the t-1 means the last token. So that way, you probably can't guess which set of tokens are green or red, because it changes after every single generation. Now, just to be clear, for the purposes of me writing the code, I just kept it very simple. I'm just going to use the same hash for every single generation. So let's have a look at how I did it. So I'm going to look at watermark, and we are going to go to the top. All right, and then let's have a look at the generation first. So this watermark generator is abstraction for the Hugging Face and Torch models, and it's really just here to simplify and remove some boilerplate code. So what I have is the top K and top P parameters, which should be familiar for people who run local models. I'm just using that to constrain the tokens that are generated, rather than considering every single token at every single turn. And then I have the generate function, and I've just abstracted it away where we can use our sample with watermark, which is this line here, so that we can write and just focus on this sampling algorithm rather than worrying about all the other intricacies. So back to the watermark generator, this kind of approach, as we said, what we want to do is we want to have our green tokens that we have here, right? So we want to see and apply our hash function, which is the g-score function, maybe poorly named. And then we want to take the set of green tokens, and if we have any green tokens, as is this line, then we want to boost the probability of the green tokens. And then for the not green, i.e. red tokens, we want to decrease the probability. And then we want to calculate the probabilities by calculating the softmax, which is what we have over here. This is a probs over the probs.sum. We can see that this is a RNG.choice, so we are sampling with these probabilities as a weight. So based on this, we can then generate with this kind of approach. Finally, how do we check whether something has this particular hash or has this particular watermark? Well, it's quite straightforward. We just count the number of green tokens and red tokens, and we can easily apply. That's what the sum function is over here. That's what the sum here is, right? So that's just counting up all the green tokens, and then we can use a transformation, assuming normality, to calculate the z-score. So let's have a quick look at what this would look like. I actually already have it on screen because I generated it before. And the question or the answer to the thing that I just said is that for the generations, the first two are generated with a watermark and the last one is generated without a watermark. So the first one is with one particular seed and the second one is with a different seed. And I wanted to show that so that you could see how that affected the Z-scores. Now, it's maybe a little bit difficult to see, but the plain output definitely has less green tokens than the other two. So when we look at the Z-score for the watermark with the correct key, we have a Z-score of 3.6. For the second scenario where we used a different seed, so it is watermarked, but then we try to apply the Z-score with the wrong seed, you get a Z-score of 0.47, which is typically not within the realm of something that is significant. Normally, you look at something like 1.65 or 1.95, 1.65 or 1.96, depending on what you're looking at for the probability distribution. And similarly for plain, it is just negative 0.14. Now, if we chop up the sentences, so these are like the sentence endings, and we just look at like the sub-sentences, you can also see the Z-scores here, and it's pretty consistent for the for the watermarked version. For the watermark with the incorrect key, you can see it's consistently not scoring these numbers, and similarly for the plain text one, it is also substantially lower. So all of this just shows you, even with this perhaps rudimentary approach, you can identify a watermark, and it has several kind of nice properties. One of them is you don't need to know the generation to compute the watermark. You just need to know whether something is a green or a red token, and you can easily compute the Z-score. So what's the second approach that we want to look at? Let's have a look at how DeepMind did theirs. So DeepMind did theirs with their SynthID slightly, it's more of an extension to the green-red token approach. So rather than just at the generation time have one single set of green and red tokens, instead they have multiple hashing functions to have zeros and ones for each of the items. So that's what we have on this side of the screen here. We have 3 different hashing functions, and they operate in 3 different ways. Then at the generation time, one of the key differences is rather than just having one function and then drawing with with those probabilities, we instead put them in a tournament. So what we do is we randomly pair each of the tokens up together and apply the first hashing function. If there's a 1 and a 0, we take 1 as the winner. If they are a tie, then we just choose 1 at random. Then for the second round of the tournament, we use the second hashing function and do the same thing. And similar with the third hashing function, and we do the same thing. If you have enough hashing functions, this is a sort of like a binary search, I suppose. It will go down very, very quickly. But even if you don't, you can just keep the last set and then do the same kind of like weighted sampling that we did before. So this is a different kind of approach that that you can use to combine these hashing functions. Now, what is interesting is in terms of the scoring for this, you actually use this very same, the same kind of approach to calculate the particular score. All you do is you take each of the hashing functions and you treat them standalone, and you just calculate the mean of occurrence for all of these hashing functions. Now, maybe the astute or the astute listeners will say, well, there's surely a better way of doing this. Yeah, the paper goes through it in the appendix. They have like some details about like how you might do a weighted version of this, and also how you might do some machine learning on this. And maybe we'll just quickly scroll down to the bottom to click on the appendix so that we can see it. Or maybe I'll go and search it. Appendix. Oh. But yeah, it was certainly there. I think in general, what is interesting is that it was just good enough to not worry about it. Yeah. Okay, so let's have a look at the implementation. So for the implementation, we will go back to our trusty editor, and much in the same way, we can go and look at the sampling approach. So it's a little bit more complicated, but not so much. So firstly, we have our tournament sampling bit. And the key thing is that we want to sample layer by layer. And as I said, G-score is our hashing function. And for each one, we just need a different seed when we compute the hash, right? And the other thing is we just want to combine them together and sample them, which is like pair them up and then combine them to determine the winner, and then keep getting them until they're smaller and smaller based on the survivors. In this particular case, once we have the survivors, if it's just one, then we just return it. But if there were more than one, I just took a random sample, which I think is actually the way the paper did it, as opposed to taking a weighted sample. But regardless, I don't think it doesn't really matter the approach, because they've shown, and we will show that it is actually quite effective way of doing it. So then the final implementation, yeah, it's fairly straightforward. You just sample with a tournament sample, a similar kind of function signature that we showed before. And then for the hashing, yes, all you need to do is you calculate again the number of times the tokens appeared for each of the hashing, each of the hashes, and then you add them all up, and then you can calculate some kind of z-score again. In this particular case. So then if we go and have a look at the run, I think this output is more interesting because you'll be able to see some different colors. So how I colored it was that it is based on like it's based on the provided score, i.e. like the total of the Z scores, the G scores, sorry. And I colored it so that if it landed in the bottom 50 percentile, it will be white. If it was 50 to 75, it will be green. If it's 75 to 90, I should have made it yellow, but maybe yellow is not coming up. And the last one is 90 plus, which is what this is supposed to say. But what you can begin to see is that there should be, maybe it's a little bit difficult to see. There should be like more greens and reds for the top one as opposed to the plain output. So even in this kind of like simplistic case, you can see that with the watermark of the correct key, you do get a much higher z-score than the other approaches, and it's consistently higher as well. So 3-2, and then these ones are consistently lower. Yeah, so this has been quite a long video for me, but hopefully it was interesting. So that is at a high level how we can do our watermarking for text. We do recap. We have our green and red approach, which is from the ICML paper in 2023, and then the SynthID approach from DeepMind. it just extends that by allowing you not to just have one hashing function, but you can have multiple. And then how it works again is you take the tournament approach that we had up here, quickly find it, and then it just pairs them up randomly at each round, and then for each round it applies a different hashing function, and then selects the winner from there until finally you get the last you get the last token. So this kind of approach, even though it's very simplistic, it still works very, very well, and you can still calculate the score. They called it the G score. Well, I call it the G score. But yeah, you can still calculate this by just taking account of how many times the tokens landed in the green buckets for each of the hashes. So hopefully you learned something. I actually had a lot of fun researching this and thinking about this and just playing around with the implementations, and hopefully you can go and try to implement this yourself as well.